On a seemingly unremarkable winter day, January 16, 1943, the freshly minted SS Schenectady lay peacefully moored at a dock within the bustling port of Portland, Oregon. This vessel, a brand-new Liberty ship, had barely seen 10 weeks of existence, having just emerged from the innovative Kaiser shipyards. No hostile enemy action threatened her robust frame, nor did any tempestuous gales lash at her hull. The morning air was tranquil, and the harbor waters remained placid. Then, without any discernible warning, a sharp, resounding crack reverberated across the expanse of the harbor. In mere moments, the entire ship catastrophically fractured completely in two, its sturdy hull cleaving from the uppermost deck down to the keel, as if severed by an unseen, razor-sharp blade. Startled sailors scrambled frantically as the bow and stern sections dramatically sagged in opposing directions, the ship's very backbone having been broken while it was tied securely to the safety of the pier. The unfortunate Schenectady was not an isolated incident in this baffling maritime phenomenon. During that same harsh winter, the SS John P. Gaines also tragically disintegrated in calm, benign seas. The SS Manhattan, a T-2 tanker constructed using identical, mass-production methodologies, developed such a severe crack that its terrified crew were compelled to abandon ship in a state of sheer panic. Between the years 1943 and 1944, a staggering number, over 2,500 Liberty ships, reported grave structural infirmities, extensive hull cracks, pronounced deck fractures, and utterly catastrophic splits. At least 19 vessels succumbed entirely, breaking completely in half. A truly chilling statistic reveals that 3 simply vanished without a trace at sea, disintegrating with such alarming rapidity that their crews were unable to even transmit distress signals. These were not the grim casualties of wartime combat. Instead, these were ships seemingly committing a bizarre form of self-destruction. The United States had staked its entire strategic fortunes on the ambitious Liberty ship program. Following the devastating attack on Pearl Harbor, which plunged America irrevocably into total global conflict, the nation found itself in desperate need of a vast fleet of cargo vessels, hundreds of them, and required with immense speed. Traditional shipbuilding methods typically consumed a laborious 8 months per vessel. The Maritime Commission simply could not afford such a protracted timeline. Henry Kaiser, a visionary industrialist with no prior experience in shipbuilding, boldly promised something truly audacious: mass-produced freighters constructed on principles akin to automobiles, designed to roll off assembly lines in mere weeks rather than many months. His Richmond, California shipyards pioneered revolutionary construction techniques, employing welding instead of the traditional riveting, utilizing prefabricated sections in lieu of laborious piece-by-piece construction, and integrating assembly line logistics shrewdly borrowed from Detroit's highly efficient car factories. By the waning months of 1942, Kaiser's prodigious yards were launching Liberty ships at an astonishing average rate of 42 days per vessel. The powerful wartime propaganda machine enthusiastically celebrated this industrial marvel. Newsreels of the era proudly showcased Rosie the Riveters, though, in a modern twist, they were predominantly welders now, transforming massive steel plates into formidable seagoing vessels at seemingly impossible velocities. The SS Robert E. Peary established an unparalleled record in November 1942, being constructed in an unbelievable 4 days and 15 hours from the laying of its keel to its momentous launch. Americans cheered this incredible feat. The Allied shipping tonnage, which had been brutally decimated by the relentless U-boat wolf packs, finally saw vital reinforcements pouring into the embattled Atlantic. Then, the ships inexplicably began to break apart, not from the expected ravages of torpedo damage or the fury of tumultuous seas, but spontaneously, catastrophically, in conditions that should have been utterly routine. Naval architects were utterly baffled by this perplexing phenomenon. The welds appeared unequivocally solid. The steel meticulously met all specified requirements. The fundamental designs were derived from proven, reliable British blueprints. Yet, Liberty ships were fracturing with the fragility of delicate porcelain teacups. The insidious cracks typically originated at sharp, angular corners, around hatch openings, at the bases of gun mounts, and within the squared-off design elements of the hull itself. Once a crack initiated, it propagated with terrifying speed through the welded hull plates, sometimes traversing the entire length of a ship in mere seconds. The Maritime Commission promptly convened emergency investigations to address this alarming crisis. Metallurgists meticulously examined failed sections of steel under powerful microscopes. Engineers diligently reviewed complex stress calculations. Naval inspectors painstakingly crawled through the labyrinthine hulls with an array of precise measuring instruments. Everyone involved desperately searched for the elusive culprit. Was it inferior steel, faulty welds, inherent design flaws, or perhaps inadequate quality control? Meanwhile, ships continued to split apart while various committees endlessly debated the possible causes. Sailors grew increasingly terrified of their own vessels, living with the chilling knowledge that the hull beneath their feet might unzip without warning in the frigid, unforgiving Atlantic waters. The celebrated miracle of mass production had devolved into a harrowing maritime nightmare, and nobody could logically explain why ships built in record time were failing in record numbers. The crucial answer, remarkably, emerged from the most improbable source: a diligent welder working on the assembly line, a person who was not officially expected to question complex engineering decisions. Bessie Hamill tirelessly worked the graveyard shift at Kaiser's Richmond Yard No. 3, one of countless women who had bravely flooded into shipyard work after the men were deployed overseas. She had been welding immense hull sections for 8 months, a duration long enough to observe something that the highly educated engineers had apparently overlooked. Every single night, she watched her team weld massive steel plates following a sequence that, to her practical eye, made absolutely no mechanical sense whatsoever. Hamill observed welders commencing their work at the edges of plates and then progressing inward, or starting at one extremity of a long seam and running a continuous bead straight to the other end. As each weld cooled, the metal inevitably contracted, exerting immense pulling and warping forces on the plates. She could visually perceive the stress accumulating, watching the steel visibly distorting beneath her welding torch. When welders completed one section and moved on to the next, they were, in effect, permanently locking the destructive stress into the very structure of the ship. It was akin to tightening the central bolts on a car wheel before securely fastening the outer ones, a surefire recipe for imbalance and ultimate failure. Her foreman, adhering strictly to protocol, summarily dismissed her concerns. She was, after all, merely a welder, not a formally trained engineer. The prescribed welding sequence emanated directly from the engineering department, from men possessing college degrees and extensive naval architecture training. Hamill, however, persisted with unwavering determination. In November 1943, she boldly requested a meeting with yard supervisors, an action that constituted a clear breach of chain of command protocol and could have potentially led to her dismissal. She brought compelling samples, test plates she had painstakingly welded on her own personal time using different, experimental sequences. Some of these samples exhibited significant warping and clearly visible stress patterns. Others, however, which had been welded from the center outward in a carefully planned sequence, lay perfectly flat and true with minimal distortion. The supervisors, initially skeptical, became progressively intrigued by her compelling evidence. One supervisor reluctantly agreed to personally observe the production line during Hamill's shift. What he witnessed unequivocally confirmed her astute observations. Welders were, in essence, torturing the steel, forcing it to accept and retain stresses that it would carry for its entire operational service life. Every cooling weld created residual tensile tension within the metal. The established construction sequence meant that these internal stresses accumulated and concentrated at specific, vulnerable points, particularly at the sharp corners of hatch openings and other critical stress concentration points. When those ships then encountered the frigid, unforgiving waters of the North Atlantic, the steel's inherent properties transformed, becoming dangerously brittle. The combination of locked and residual stress and this newfound brittleness created the perfect, catastrophic conditions for sudden, violent fracture. Hamill's profound insight was elegantly simple yet remarkably effective. Welders should commence their work from the center of sections and progress outward, thereby allowing stress to dissipate harmlessly toward the edges rather than concentrating destructively in the middle. Furthermore, they should alternate welding locations to prevent excessive heat buildup in any single area. Crucially, welds should never be completed in long, continuous runs. Instead, a balanced sequence that evenly distributed cooling stresses was imperative. These were not groundbreaking metallurgical theories. Rather, they were practical, empirical observations gleaned from someone who genuinely worked with the material every single day, who could feel the metal subtly move under her torch and accurately recognize the dire consequences of improper technique. By December 1943, her groundbreaking observations had reached the attention of Henry Kaiser himself. He was confronted with a brutal and difficult choice. The monumental Liberty ship program was already under intense congressional scrutiny due to the escalating cracking epidemic. Admitting that the construction sequence, and not merely the steel quality or weld integrity, was the fundamental underlying problem meant acknowledging that every single ship built thus far harbored systematic flaws inherently baked into their very hulls. It also implied the necessity of temporarily slowing down precious production to retrain thousands of welders. It would necessitate a complete redesign of the entire assembly process. However, it also offered the potential to definitively solve the pervasive fracture crisis that threatened to completely undermine America's entire maritime logistics chain. Kaiser, to his immense credit, did not hesitate. He swiftly authorized immediate testing of Hamill's theories, even pulling an entire hull section directly from the active production line for experimental reconstruction. The very metallurgists and engineers who had spent months meticulously analyzing failed ships were now, remarkably, taking instruction from a night shift welder who had never once seen the inside of a college classroom. The results of these tests were both damning and revolutionary in equal measure. When Kaiser's metallurgists meticulously examined hull sections constructed using conventional sequences versus those built employing Hamill's innovative methods, the difference was both measurably significant and dramatically apparent. Residual stress gauges revealed that traditionally welded sections carried immense internal tensions, often exceeding 30,000 pounds per square inch, concentrated precisely at critical structural points. Conversely, Hamill's carefully sequenced sections effectively distributed those stresses across much broader areas, with peak readings barely reaching 12,000 psi. The steel itself was absolutely identical. The welds were chemically indistinguishable. Only the precise order of operations had been altered, yet the fundamental structural integrity improved by factors that the engineers initially found difficult to believe. The intricate physics behind these catastrophic failures finally became unequivocally clear. steel is not a static, inert material. Rather, it is a dynamic crystalline structure that responds profoundly to changes in temperature. When welders guide a torch along a seam, they generate a localized temperature that can exceed an astonishing 2,500 degrees Fahrenheit. The metal within that intensely heated zone expands dramatically. As the weld subsequently cools, it contracts, but the surrounding, colder steel rigidly constrains that contraction. The inevitable result is residual tensile stress, permanently locked into the structure, unless the welding sequence is specifically designed to allow this stress to redistribute effectively. Liberty ships were suffering from a phenomenon metallurgists term brittle fracture propagation. The specific type of steel utilized in their hulls, a carbon steel designated as shipbuilding grade, performed adequately in warmer waters. However, it underwent a critical and dangerous transformation in the near-freezing temperatures of the North Atlantic. Below approximately 40 degrees Fahrenheit, the steel's crucial ductility dramatically collapsed. Normally, metal absorbs stress by deforming slightly, bending rather than fracturing. Cold steel, however, loses that vital flexibility. It becomes brittle, behaving more like fragile glass than the tough, resilient material welders worked with in California's mild shipyards. When this brittle steel encounters concentrated residual stress at a sharp corner, such as the square edge of a cargo hatch, the laws of physics take over with brutal efficiency. A microscopic crack initiates. In ductile steel, that nascent crack would typically arrest itself, absorbed by the material's inherent ability to yield. In brittle steel under intense tension, however, the crack transforms into a sprinting fracture. The immense energy stored in those residual stresses provides the devastating fuel for the crack to propagate relentlessly. Sharp corners, acting as potent stress concentrators, multiply the local stress by factors of 3 or even more. The crack then accelerates, sometimes exceeding the speed of sound within the steel itself, racing through the hull before bulkheads or frames can possibly arrest its destructive path. The catastrophic failure of the SS Schenectady, while shocking at the time, became entirely comprehensible upon closer examination. Constructed during the bitter cold of early winter, its structural integrity was compromised by welding sequences that inadvertently maximized internal stresses, leaving its hull burdened with tens of millions of pounds of latent tension. When the Portland morning temperature plummeted to a frigid 28 degrees Fahrenheit, the steel, already under immense duress, became dangerously brittle. A critical stress concentration, located precisely at a hatch corner, served as the initiation point for a devastating crack. This fissure then followed an unobstructed trajectory through the continuously welded deck plates, encountering no riveted seams to impede its progress, nor any engineered stress relief brakes to halt its advance. The fracture consumed the vessel in a matter of seconds, unleashing decades of accumulated energy in a single, calamitous event that tore the ship apart. Conversely, traditional ships, meticulously assembled with rivets, did not typically succumb to this particular mode of failure, and understanding this distinction shed considerable light on why the then nascent practice of welding appeared to be fraught with peril. Riveted construction, by its very nature, is characterized by inherent discontinuities. Each individual riveted plate functions as a discrete structural element. Consequently, any cracks that might originate within one plate would invariably encounter a riveted seam, where their propagation would be arrested. The overlapping plates and the mechanical fasteners, such as rivets, effectively formed natural crack arresters. Welded ships, however, presented a fundamentally different structural paradigm, being continuous entities. A crack, once initiated in a single plate, could traverse unimpeded through hundreds of feet of welded seams. The very efficiency that expedited the construction of welded ships simultaneously rendered them susceptible to catastrophic failures that riveted vessels were inherently protected against. This problem was further exacerbated by the design of the Liberty ships, which featured distinctive squared-off corners. British maritime architects had specifically incorporated these hard corners to facilitate more efficient cargo loading and unloading. Regrettably, no one at the time had adequately considered that sharp internal corners act as potent stress concentrators, capable of multiplying applied loads by enormous factors. Each wave that caused the hull to flex and strain sent acute stress spikes through these vulnerable corners. When these localized stress intensifications were combined with the residual stresses locked in by the welding process and the brittle nature of the steel at low temperatures, these corners transformed into prime crack initiation sites, lying in wait for the precise confluence of conditions to trigger a catastrophic structural collapse. Henry Kaiser, a visionary industrialist, grasped the profound implications of these unsettling test results for the vast industrial empire he had meticulously built and, more broadly, for the Allied war effort itself. In the pivotal month of January 1944, he made a momentous decision that would either unequivocally vindicate his revolutionary industrial methods or irrevocably expose him as a reckless profiteer who had callously dispatched thousands of Allied sailors to sea aboard inherently defective vessels. He issued an unequivocal order for a complete cessation of Liberty ship production at his Richmond Yard 2 facility. Concurrently, he redirected an immense allocation of resources toward the development and construction of an entirely new class of merchant vessel, christened the Victory ship. This was not merely a superficial modification or a minor design tweak. It represented a fundamental and comprehensive redesign, meticulously conceived around the groundbreaking welding observations made by Bessie Hamel and the invaluable, albeit hard-won, lessons painfully inscribed in the fractured hulls of ships scattered across two vast oceans. The sheer audacity of this gamble was staggering. Liberty ships, at that critical juncture, were still desperately needed to sustain the Allied war machine. German U-boats had, since the outbreak of hostilities in 1939, relentlessly sent over 2,000 Allied merchant vessels to the frigid depths of the ocean. The impending invasion of Europe, still several months away in early 1944, would necessitate the most expansive and complex amphibious logistics operation ever conceived in human history. Every single ship, therefore, held immense strategic importance. Yet, Kaiser was making an audacious wager that he could successfully implement Hamel's meticulously sequenced welding system, fundamentally redesign the hull to completely eliminate all stress concentrations, significantly enhance the steel specifications, and somehow, against all odds, maintain the breathtaking production speeds that already bordered on the miraculous. His competitors, observing this radical shift, were convinced he had irrevocably lost his mind. Meanwhile, congressional investigators, ever vigilant, began to sharpen their figurative knives, poised to crucify him should production falter or collapse under the weight of this ambitious undertaking. Kaiser's dedicated team of engineers systematically reversed their approach, meticulously working backward from every identified point of failure. Every sharp, squared-off corner that had characterized the original Liberty ship design was painstakingly replaced with gracefully rounded transitions, effectively mitigating stress accumulation. The hatch openings, notorious for being the genesis of countless cracks, underwent a radical redesign, incorporating generous, radiating curves that successfully eliminated the stress multipliers which had previously transformed normal operational loads into catastrophic fracture initiators. The thicknesses of the deck and hull plates were meticulously recalculated, not with the primary objective of simply adding more strength, but rather to ensure that the stress distribution harmonized perfectly with the newly implemented welding sequences. Furthermore, structural frames were strategically repositioned to align with natural stress relief points within the design, rather than inadvertently working against the carefully planned welding patterns. The very composition of the steel itself underwent a significant transformation. Kaiser's astute metallurgists specified a new alloy designation, meticulously formulated to possess dramatically improved low-temperature toughness, a critical property for ships operating in frigid waters. The carbon content was subtly reduced, while the manganese content was judiciously increased to enhance ductility. Small, yet impactful, additions of nickel, a notoriously expensive and heavily rationed metal typically reserved for armor plating, were rigorously justified. Demonstrable evidence showed that even a modest 0.25% nickel content dramatically bolstered the steel's resistance to brittle fracture. Initially, the Maritime Commission expressed reservations regarding the increased cost associated with this upgraded alloy. However, Kaiser effectively countered these objections by presenting compelling calculations that unequivocally demonstrated that preventing the loss of just one ship would more than offset the additional cost of the upgraded steel for an entire fleet of 50 vessels. Convinced by this irrefutable economic logic and the imperative for safety, the new steel specification received official approval in March 1944. Following this crucial material upgrade came the monumental undertaking of comprehensively retraining the vast workforce. By early 1944, the Richmond shipyards alone employed an astonishing 90,000 workers. Thousands of these individuals were welders who had acquired their trade through intensive, weeks-long crash courses, mastering just enough technique to lay straight beads at high production speeds. Now, however, they were confronted with the daunting task of understanding intricate concepts such as sequencing, stress relief, and thermal management. In response, Kaiser established dedicated welding schools directly within the shipyards, strategically pulling highly experienced welders, such as Bessie Hamill, off the production lines to serve as instructors. Each welder was issued a precisely numbered sequence card for every hull section they worked on. This card dictated the exact order of operations. Weld number 1 here, number 2 there, never allowing for deviation from the prescribed order. The existing prefabrication system was dramatically expanded and refined. Instead of the previous method of welding large sections directly on the ways, where controlling sequencing was inherently challenging, Kaiser's meticulous planners ingeniously broke down Victory ships into much smaller, more manageable modules. These modules were then constructed in specialized, dedicated workshops. For instance, a single bow section might comprise as many as 50 separate prefabricated assemblies, each meticulously welded under strictly controlled conditions using optimal sequences. Crucially, these assemblies were then stress-relieved in heating ovens before their final integration. This innovative modular approach provided welders with the flexibility to work from the center of each small section outward, precisely as Hamill had so effectively demonstrated, unencumbered by the spatial and logistical constraints of assembling an entire hull simultaneously. The skeptics found ample ammunition for their criticisms when the keel of the very first Victory ship was laid in February 1944. Its construction required 18 days to complete, a noticeably slower pace than the established records for Liberty ships. Critics were quick to declare that Kaiser's yards were no longer performing miracles. They were merely constructing ships at an impressive, but no longer astonishing speed. The second Victory ship, while an improvement, still took 16 days. Critics, seizing on these figures, declared the entire program a resounding failure, citing this as irrefutable proof that achieving both quality and speed in shipbuilding was fundamentally incompatible. Kaiser, however, steadfastly ignored their pronouncements. His focus was not solely on construction times. He was meticulously scrutinizing the crack inspection reports. The initial 2 Victory ships, upon thorough post-construction inspection, revealed 0 stress cracks. This was not a reduction in cracks. It was an absolute absence of them, a truly remarkable achievement. By April 1944, Richmond Yard 2 had undergone a profound transformation, evolving into a finely tuned choreography of steel, intense heat, and human coordination, a spectacle that would have been deemed utterly impossible just 2 years prior. The shipyard no longer resembled a traditional shipbuilding facility. Instead, it bore a striking resemblance to an enormous assembly plant, complete with distinct fabrication zones that continuously fed a central assembly area where hulls miraculously took shape with astonishing rapidity. Kaiser had ingeniously adapted Henry Ford's revolutionary moving assembly line concept. However, instead of the product itself moving, specialized teams rotated through stationary construction stations at precisely timed intervals, bringing their expertise to each stage of the build. The intricate process commenced within the prefabrication sheds, vast covered structures where welders meticulously worked on hull sections no larger than 30 feet in any dimension. Each individual section was accompanied by a specific sequence card, detailing the exact order of operations. For instance, a bottom plate assembly might necessitate 47 individual welds, each precisely numbered and color-coded for clarity. Welders initiated their work at position 1, which was invariably the geometric center of the section, and systematically progressed outward in either a spiral or radial pattern. Supervisors diligently patrolled the floor, armed with comprehensive checklists, ensuring that no welder inadvertently skipped ahead in the sequence. After every 10 welds were completed, the section was carefully transferred into a specialized stress relief oven, where it was heated to an impressive 2,100 degrees Fahrenheit and then allowed to cool slowly. This crucial annealing process permitted the steel's crystalline structure to relax, effectively dissipating residual stresses before they could accumulate to dangerous and compromising levels. The steel itself arrived at the shipyard already pre-cut and preformed from rolling mills that had been meticulously retooled specifically for the ambitious Victory ship production program. Unlike the construction of Liberty ships, where yard workers were responsible for cutting and shaping plates on site, Victory ship components arrived ready for immediate assembly, minimizing on-site fabrication. Curb bow sections, for example, came preformed to exact specifications, ensuring precise fit and finish. Deck plates were delivered with pre-drilled bolt holes, facilitating temporary alignment during the assembly process. Frame sections were supplied as pre-welded assemblies, further streamlining construction. This extensive preparation work, meticulously executed in controlled factory environments, effectively eliminated numerous variables and ensured a high degree of consistency across thousands of individual components. The assembly process on the building ways followed a radically different and innovative sequence compared to Liberty ship construction. Instead of the traditional method of starting at the keel and building upward, Victory ships were assembled in large, integrated modules that converged almost simultaneously. The engine room section, the various cargo hold sections, the bow, and the stern were all constructed in parallel, concurrently with other components. These massive modules were then lifted by colossal gantry cranes and precisely positioned in a single, highly coordinated operation. On May 12, 1944, Yard 2 executed its most ambitious assembly feat to date, 17 major modules, collectively representing an astonishing 85% of a complete hull, were meticulously positioned and aligned in an astonishingly brief 11 hours. Welders then proceeded to connect these modules using the same center-outward sequences, but now they were joining stress-relief sections rather than building stress sections from scratch, a critical distinction for structural integrity. The ambitious 5-day timeline for ship completion became a tangible reality through the relentless and meticulous optimization of every single minute within the production schedule. Night shifts were strategically employed to preposition all necessary materials for the day shifts, ensuring seamless transitions. Specialized teams were dedicated solely to checking alignment and scrutinizing weld quality, proactively identifying and rectifying errors before they could propagate and lead to more significant issues. Mobile cranes operated on precisely scheduled routes, delivering components to designated welding stations within tight, 5-minute windows. Welders worked in carefully planned rotations, 30 minutes actively on the torch, followed by a 10-minute rest period. This system was designed to maintain consistent quality by preventing the fatigue-induced errors that had plagued marathon welding sessions in the past. Kaiser implemented what he termed the critical path method, a sophisticated system for tracking which tasks constituted bottlenecks and which could proceed in parallel. If, for instance, frame installation was ahead of schedule but pipe fitting was lagging, he would immediately reallocate workers, thereby maintaining a delicate balance across all construction phases. Every delay, every single deviation from the meticulously planned schedule, was rigorously documented and thoroughly analyzed. Morning meetings were held daily to review the previous day's performance, with the explicit goal of identifying proactive solutions before minor problems could escalate into catastrophic delays. The pinnacle of this relentless optimization was achieved on June 27, 1944, when the SS Benjamin Warner, Victory Ship Hull No. 23, was completed from the laying of its keel to its sea trials in an astounding 5 days and 11 hours, setting a new benchmark for shipbuilding efficiency and speed. The construction of the SS Warner was an extraordinary feat, completed in a mere 5 days and 11 hours. This was no stripped-down, bare-bones prototype, but a fully operational, battle-ready cargo vessel, meticulously outfitted with robust defensive armaments, comprehensive electrical systems, a meticulously engineered engine room, and every crucial connection, specifically every weld, executed in strict adherence to the novel stress relief protocols. Remarkably, she exhibited no signs of stress cracks, and a thorough post-construction inspection confirmed that her structural stress levels remained comfortably within normal operational parameters. When the Warner embarked on her demanding shakedown cruise, she demonstrated impeccable performance, navigating challenging conditions that would have undoubtedly caused catastrophic fracturing in earlier Liberty ships. The rapid assembly of the 5-day Victory ship transcended mere construction speed. It heralded a profound paradigm shift in how intricate machinery could be fabricated when advanced engineering principles were seamlessly integrated with the pragmatic realities of industrial construction. Bessie Hamill's astute observations had catalyzed a sweeping, systematic transformation within the entire shipbuilding industry. The Victory ships that emerged from Kaiser's radically redesigned production system were, at their core, fundamentally distinct vessels compared to their Liberty ship predecessors. While a casual observer might perceive them as similar cargo carriers fulfilling identical logistical missions, the crucial differences permeated every aspect of their being, commencing at the molecular composition of their materials and extending through every nuance of their design and construction methodology. Where the Liberty ships had been conceived as urgent, temporary stopgaps to address immediate wartime shipping needs, the Victory ships represented meticulously engineered solutions, specifically designed to mitigate every failure mode that had tragically claimed the lives of countless sailors, whose blood stained the cold Atlantic waters after their fracturing hulls succumbed to the stresses of the ocean. The introduction of an improved steel specification proved absolutely pivotal. This innovative alloy, aptly termed killed steel, due to the precise addition of aluminum during its production to effectively remove oxygen, exhibited dramatically enhanced toughness, particularly in frigid temperatures. Extensive laboratory analyses revealed that the critical transition temperature, the precise point at which steel undergoes a perilous transformation from ductile, flexible behavior to brittle, fragile rigidity, had plummeted from approximately 40 degrees Fahrenheit in Liberty ship steel to a mere 5 degrees. This significant 35-degree improvement meant that Victory ships were able to retain their essential structural flexibility and resilience even in environmental conditions that rendered Liberty hulls dangerously fragile and prone to catastrophic failure. Although this superior material incurred an 8% cost premium per ton, the resultant gain in performance and safety was, quite simply, incalculable. Every intricate structural detail within the Victory ship was a direct embodiment of the newfound understanding regarding stress concentration and the mechanics of crack propagation. The seemingly minor aesthetic modification of rounded hatch corners, for instance, delivered a substantial engineering benefit, reducing localized stress concentrations by more than 60%. Detailed engineering calculations conclusively demonstrated that the sharp, unforgiving 90 degrees corners prevalent in Liberty ships generated stress multipliers ranging from 3.5 to 4 times the nominal hull stress. In stark contrast, the Victory ship's generously curved radii consistently maintained stress multipliers below 1.8. In practical operational terms, this meant that a powerful wave impact that would invariably initiate a devastating crack in a Liberty ship would merely cause a Victory ship's hull to flex safely within its normal elastic limits, absorbing the energy without critical damage. Furthermore, the hull plates themselves were meticulously installed with integrated crack arrestor features strategically woven into the very fabric of the structure. Instead of relying on continuous welds that stretched for hundreds of feet, Victory ships purposefully incorporated riveted seams at predetermined, strategic intervals. These hybrid connection points served as intentional discontinuities, acting as critical barriers where a propagating crack would inevitably encounter a mechanical joint, thereby dissipating its energy and potentially halting its destructive path before it could compromise the entire hull. This innovative design philosophy consciously accepted the possibility of crack initiation, but engineered multiple, redundant arrest mechanisms to actively prevent catastrophic propagation. It represented a proactive approach to defensive engineering, meticulously planning for potential failure modes rather than operating under the precarious assumption of flawless perfection. Structural frames were intelligently doubled at all critical stress points, thereby creating essential redundant load paths. This ingenious design ensured that if one frame were to develop cracks, adjacent frames were immediately capable of shouldering the additional load, maintaining structural integrity until necessary repairs could be effectuated in port. Liberty ships possessed no such redundancy. A single frame failure often precipitated a progressive collapse, as loads were disastrously redistributed to already overstressed adjacent structures. Consequently, Victory ships possessed the remarkable ability to sustain damage that would undoubtedly sink a Liberty ship, yet remain operational, capable of limping to port uncompromised but still functional structures. The sophisticated welding sequences, derived directly from Bessie Hamill's pivotal observations, were rigorously codified into highly detailed procedures that meticulously governed every single joint throughout the vessel. The comprehensive procedure manuals, often running to hundreds of pages, specified not only the precise sequence of welds, but also the critical thermal management protocols to be observed between successive passes. Welders were meticulously trained to continuously monitor the interpass temperature, which is the heat level of the base metal between consecutive weld passes. If the steel's temperature exceeded 400 degrees Fahrenheit, all work was immediately halted until it had naturally cooled. This stringent control effectively prevented the cumulative heat buildup that had caused massive distortion and internal stresses in Liberty ship construction, where welders sometimes worked continuously on long seams, superheating the steel into warped, stress-riddled configurations. Quality control, in this new era of shipbuilding, became nothing short of obsessive. Every completed weld underwent meticulous magnetic particle inspection, a refined technique where finely dispersed iron powder, under the influence of magnetic fields, would visibly reveal even microscopic cracks invisible to the naked eye. Ultrasonic testing was employed to scrutinize internal weld quality, guaranteeing full penetration and the absence of any hidden voids or imperfections. X-ray inspection was reserved for critical structural welds, producing invaluable permanent photographic records that attested to the absolute integrity of each weld. Vessels were strictly prohibited from launching until highly trained inspectors had thoroughly certified that every single weld met the exacting specifications. The initial rejection rate was notably high, with nearly 15% of welds failing inspection in the very first Victory ships. However, welders rapidly assimilated the new techniques and procedures. By the middle of 1944, rejection rates had plummeted to below 3%, a powerful testament to the efficacy of the rigorous training programs and the crystal-clear clarity of the newly implemented procedures. The ultimate validation of these innovations emerged definitively in operational service. Between June 1944 and the cessation of hostilities in August 1945, an impressive fleet of 531 Victory ships entered active duty. Crucially, not a single one of these vessels suffered a catastrophic hull failure. Minor cracks were observed in only a handful of ships, localized stress concentrations that vigilant inspection teams caught and addressed before they could propagate into serious issues. These minor cracks were promptly repaired using the identical stress relief welding procedures, and the ships were swiftly returned to service. The contrast with the performance of Liberty ships was stark, absolute, and undeniably damning. The profound human arithmetic of Victory ships versus Liberty ships unfolded across two vast oceans during 1944 and 1945. A narrative written in countless lives saved and critical missions successfully completed, missions that would have undoubtedly culminated in disaster had earlier, less robust vessels been employed. A compelling example of this resilience occurred in April 1945, when the SS Unthinkable, a Victory ship, struck a mine off the coast of Okinawa. The ensuing explosion tore a gaping 20-foot gash in her hull below the waterline. The crew, acutely aware of the tragic history of Liberty ships, braced themselves for the expected catastrophic crack propagation that had so often doomed their predecessors. Instead, to their profound relief, the fracture abruptly halted at the first strategically placed riveted crack arrestor seam. The Unthinkable remarkably made port under her own power, underwent repairs in an astonishing 6 days, and was promptly returned to active service. In stark contrast, the SS Richard Harvey, a Liberty ship suffering comparable damage from a mine strike in February 1945, cracked longitudinally for over 90 feet, ultimately broke her keel, and tragically sank in a mere 14 minutes, resulting in the devastating loss of 37 crew members. The sheer logistical demands of the Pacific campaign would have been utterly impossible to meet. without the unparalleled reliability demonstrated by Victory ships. By June 1944, American forces were relentlessly advancing across the Central Pacific, pushing steadily toward the Philippines and ultimately toward the Japanese home islands. Each successive island advance necessitated the movement of millions of tons of vital supplies across thousands of miles of vast ocean. While Liberty ships could physically undertake these voyages, their inherent structural fragility mandated significantly reduced cargo loads in rough seas, slower transit speeds to minimize hull stress, and the ever-present, terrifying risk of catastrophic structural failure far from any hope of rescue. Victory ships, however, routinely operated with full cargo loads at their design speed of 15 knots, a crucial 3 knots faster than Liberty ships, navigating through notoriously typhoon-prone waters without the paralyzing fear that a cold night and turbulent seas would inevitably split their hulls. The compelling numbers unequivocally underscored this narrative of success. Between D-Day in June 1944 and VJ Day in August 1945, Victory ships collectively transported over 18 million tons of essential cargo, with absolutely zero losses attributed to structural failure. They routinely operated in the treacherous North Atlantic convoys, where water temperatures frequently plunged below 35 degrees Fahrenheit, conditions that had previously fractured dozens of Liberty ships. They also fearlessly plied the arduous Arctic routes to Murmansk, delivering critical Lend-Lease supplies to the Soviet Union, regions where seawater temperatures near freezing had rendered Liberty ships terrifyingly vulnerable. The SS Hobart Baker, a Victory ship, completed an astonishing 17 Murmansk runs without developing a single stress crack. In stark contrast, the Liberty ship John Walker, traversing the identical route, developed severe cracks on her second voyage and was permanently withdrawn from Arctic service, a damning indictment of the earlier design. The psychological transformation of crew morale was palpable when sailors transferred from the precarious Liberty ships to the robust Victory vessels. Oral histories, meticulously collected after the war, vividly reveal the immense psychological burden of serving aboard ships notoriously known to spontaneously break apart. Merchant mariners frequently recounted experiencing constant, gnawing anxiety, particularly during cold weather conditions. Sleep was an elusive luxury, when every groan or creak of the hull might signal an impending fracture. Some sailors, overcome by fear, actively requested transfers or simply refused to ship out on specific Liberty vessels with documented histories of cracking. Victory ships, however, profoundly restored confidence. Crews were emboldened to push these vessels hard, knowing implicitly that the ships were engineered to withstand the punishment. This newfound confidence directly translated into enhanced mission effectiveness, significantly faster turnarounds in port, a greater willingness to sail in marginal weather conditions, and more aggressive maneuvering tactics when confronted with aerial attacks. The fierce Battle of Leyte Gulf in October 1944 served as a dramatic testament to the Victory ship's extraordinary combat resilience under conditions that would have utterly devastated their Liberty ship counterparts. 16 Victory ships valiantly supported the massive invasion fleet, tirelessly hauling vital ammunition, aviation fuel, and other critical supplies through relentless kamikaze attacks amidst turbulent typhoon conditions. The SS Kyle Johnson, for instance, sustained significant near-miss bomb damage that visibly buckled her deck plates and cracked 3 frame sections. Yet, with remarkable fortitude, she continued operations, unloading her crucial cargo under direct fire for 4 arduous days before finally withdrawing for necessary repairs. The inherent structural redundancy and ingenious crack arrest features prevented this localized damage from cascading into a catastrophic structural failure. In stark contrast, Liberty ships suffering similar damage typically had to be abandoned, as their cracks propagated uncontrollably, leading to inevitable loss. The ramifications of unchecked failure propagation quickly extended beyond mere structural integrity. A stark and undeniable economic assessment underscored the rationale for change. Each Liberty vessel, for instance, commanded a construction expenditure of approximately $2 million. In contrast, its successor, the Victory ship, incurred a cost of $2.6 million, representing a 30% increase in initial outlay. However, historical data up to 1944 revealed a troubling reality. A Liberty ship faced a 4.6% probability of experiencing a catastrophic structural collapse during its operational lifespan. Such devastating incidents typically claimed the lives of an average of 18 mariners per occurrence and obliterated valuable cargo shipments, with losses estimated at 3 to 5 times the vessel's original building price. The Victory ship, remarkably, boasted an unblemished record of 0 structural failures. This crucial distinction meant that the seemingly higher additional $600,000 investment in its construction was swiftly recouped within the initial half-year of its deployment, purely through the profound reduction in operational hazards and the subsequent decrease in insurance liabilities. As the global conflict drew to a close, a poignant and somber adage circulated among merchant mariners, succinctly encapsulating the profound divergence between the two ship types. Liberty ships were fabricated by the mile and dismantled by the yard, whereas Victory ships were meticulously crafted by the inch and gauged by the year. This seemingly small distinction, represented by those precious inches, encompassed a suite of critical engineering advancements. The scrupulous adherence to precise welding sequences, an unyielding commitment to rigorous quality control measures, and the strategic integration of ingeniously designed crack arresters. These painstaking efforts translated directly into vessels capable of enduring decades of reliable service, a stark departure from the anxiety-ridden voyages of their predecessors, where crews often offered desperate supplications each time the hull emitted a disquieting groan amidst the frigid ocean swells. In 1946, Bessie Hamill quietly transitioned back into civilian existence, her departure marked by a conspicuous absence of public celebration or official accolades, save for a solitary commendation letter from her shipyard supervisor. She was never adorned with a medal, nor was she ever summoned to present her findings before the esteemed chambers of Congress. Her name remained conspicuously absent from the myriad technical treatises that subsequently chronicled the profound welding revolution she had undeniably initiated. Instead, the established engineering community readily assimilated her groundbreaking insights, diligently rearticulating them through the formal lexicon of mathematical equations and specialized academic parlance. These revelations were then disseminated as if they had originated from meticulous laboratory experimentation, rather than blossoming from the keen, practical observations of a dedicated night shift welder. For numerous decades thereafter, foundational welding textbooks routinely expounded upon the critical importance of stress relief sequencing, yet consistently omitted any mention of the pioneering woman who had first discerned its absolute necessity while witnessing steel plates distort beneath the intense heat of her welding torch. Nevertheless, the enduring imprint of her contributions profoundly shapes contemporary engineering practices, extending its influence far beyond the confines of naval construction. Virtually every welded assembly fabricated in the modern era, encompassing structures as diverse as towering skyscrapers, extensive pipeline networks, and robust pressure vessels, adheres to sequencing protocols that trace their direct lineage to the innovative procedures first conceived and refined at the Richmond shipyard in 1944. A testament to their efficacy, The American Welding Society's Structural Welding Code, initially promulgated in 1947, formally enshrined center outward welding sequences and stringent stress relief mandates as indispensable, compulsory standards. Decades later, during the ambitious pipeline construction endeavors across Alaska in the 1970s, engineers explicitly adopted and referenced welding methodologies derived from Victory ship practices to effectively mitigate the pervasive challenge of cold weather cracking in the harsh Arctic environment. Indeed, the very existence of the Trans-Alaska Pipeline, a monumental 800-mile artery of welded steel successfully conveying heated crude oil through perpetually sub-zero temperatures, stands as a monumental testament to the profound comprehension and application of the invaluable lessons imparted by Hamel. The principles established through Hamel's work found their way into modern bridge construction, where their importance was often underscored by tragic events. A stark example is the catastrophic collapse of the Point Pleasant Bridge in West Virginia in December 1967, an incident that claimed the lives of 46 individuals. Subsequent investigations meticulously identified residual welding stress as a significant contributing element to the disaster. It was revealed that welds performed without adherence to proper sequencing had inadvertently embedded perilous stress concentrations within the critical structural components. In the wake of this tragedy, comprehensive post-disaster code revisions were swiftly implemented, making mandatory the precise sequencing and rigorous inspection protocols that the Victory ships had originally pioneered. Consequently, every welded bridge erected since that pivotal time has incorporated these essential requirements. Even the monumental seismic retrofit of the Golden Gate Bridge in the 1990s, which involved the meticulous addition of thousands of tons of welded steel reinforcement, utilized highly advanced computer-modeled welding sequences. These sophisticated simulations were expertly optimized to minimize residual stress, representing an evolved and complex realization of the fundamental principles Hamel had so clearly demonstrated with her rudimentary hand-welded test plates back in 1943. The offshore oil industry, regrettably, absorbed these vital lessons through a series of devastating and costly experiences. The tragic Alexander Kielland platform disaster off the coast of Norway in 1980, which resulted in the loss of 123 lives when the colossal structure capsized, was partially attributed to fatigue cracks. These cracks were found to have originated and propagated from welds that had been improperly sequenced during construction. 8 years later, in 1988, the catastrophic Piper Alpha platform explosion, claiming the lives of 167 men, began with an insidious crack in a critical welded pipe connection where residual stress had dangerously accumulated. Each of these profound tragedies compelled investigators to undertake exhaustive examinations of existing welding procedures. In a recurring pattern, each subsequent inquiry independently rediscovered fundamental principles that had been unequivocally established and proven effective during the construction of Victory ships some 4 decades prior. Consequently, contemporary offshore standards now stringently mandate comprehensive stress relief heat treatment for all welds deemed critical, a direct and unmistakable testament to the pioneering use of specialized ovens that Kaiser had installed in the prefabrication workshops at Richmond. Perhaps the most demanding and critical application of stress relief welding techniques is found in the construction of nuclear pressure vessels, which are meticulously engineered to safely encase reactor cores operating under unimaginable temperatures and immense pressures. The formidable steel casings designed to contain these potent nuclear reactions simply cannot accommodate even the slightest point of crack initiation. Consequently, the welding sequences for these vital reactor vessels are meticulously choreographed with unparalleled computational precision, employing sophisticated simulations to model thermal effects and residual stresses long before the initial weld is even contemplated. Following fabrication, the entire colossal vessel undergoes an exhaustive post-weld heat treatment within colossal ovens, mirroring precisely the processes applied to Victory ship sections. This crucial step effectively neutralizes any lingering residual stresses that could potentially evolve into catastrophic failure points. It is noteworthy that the pioneering engineers who formulated these intricate procedures during the 1950s explicitly engaged in a thorough study of Victory ship construction, regarding it as an indispensable foundational reference for their own groundbreaking work. Hamill's astute observations profoundly reconfigured the fundamental intellectual framework through which engineers approach fabrication processes. Prior to the advent of the Victory ships, the realms of structural design and actual construction largely operated as distinct and often isolated domains. Engineers meticulously conceived and drafted blueprints for structures, while fabricators were tasked with their physical realization. Communication between these two critical groups regarding the profound impact of construction methodologies on ultimate structural performance was, regrettably, infrequent. The Victory ships unequivocally demonstrated that the precise sequence of fabrication was not merely ancillary, but equally as crucial as the judicious selection of materials or the inherent elegance of the structural design itself. As a direct consequence, contemporary engineering curricula now seamlessly integrate manufacturing processes as indispensable components within their core design courses. Aspiring engineers are thus indoctrinated with the vital understanding that even an impeccably conceived design, if executed with a flawed fabrication sequence, will inevitably yield results inferior to those achieved by a more modest design brought to fruition through scrupulously correct procedures. While the astonishing 5-day construction timeline was undeniably impressive in its own right, it was never, in truth, the ultimate triumph. Kaiser's shipyards possessed the capacity to sustain the accelerated pace of Liberty ship production indefinitely, ceaselessly launching vessels that, despite their outward appearance of seaworthiness, were inherently flawed and destined for eventual fracture. The genuine marvel, rather, resided in the deliberate decision to decelerate production sufficiently to ensure correctness. It was the profound courage exhibited in pausing the manufacturing line and fundamentally re-engineering entire processes, all predicated upon the insightful observations of a frontline welder, observations that directly challenged entrenched industry practices. This extraordinary readiness to attentively heed the voices of those directly engaged in production, to humbly concede that prevailing engineering theory had overlooked a critical element, and to meticulously reconfigure operational systems based on tangible, observed reality rather than rigidly defended assumptions, therein lay the true revolution. Indeed, this foundational principle is now intrinsically woven into the fabric of virtually every contemporary manufacturing methodology, from the rigorous frameworks of Six Sigma and lean production to comprehensive total quality management systems. It underscores the undeniable truth that the worker directly engaged in the process frequently perceives critical nuances that an engineer, operating from the detachment of a desk, simply cannot ascertain through calculations alone. Bessie Hamill herself passed away in 1987 in Sacramento, her obituary offering only a terse mention of her employment in wartime shipyards. Yet, her profound influence endures, silently permeating countless structures across the globe. Every towering edifice, every vital pipeline traversing unforgiving frozen landscapes, every robust pressure vessel safely containing perilous forces, and every majestic bridge gracefully spanning vast rivers. All these constructions bear her indelible legacy within their meticulously sequenced welds and precisely stress-relieved joints. They stand as a silent, monumental tribute to the unassuming Welder, who dared to question why ships were failing and resolutely declined to accept the complacent retort of, "That's just how it's done," as a sufficient explanation.